Hello all, welcome to lectures by Aparna. So today we are having Thevenin's theorem here. So I have written the theorem, but I am not going to read it now. First I will explain what it means and then I will read the theorem so that it will be easy to understand. Okay, so let's get started. For a sample network, I have taken a network like this. Now I am going to explain Thevenin's theorem on this network. Okay, so the first step that we do for this network to apply Thevenin's theorem here is that we take away this RL from this network. First, keep the load resistance aside. Okay, so we have an open circuit here. Let these terminals be A and B. The next step is to find the voltage VAB from this side. Okay, we have to find voltage VAB across this network. So let's find VAB. Voltage across A and B, VAB will be equal to, find the voltage division, use the voltage division law. So what does it say? The total voltage into the voltage across resistance R2 divided by R1 plus R2. So this is VAB. Okay, and this VAB is equal to the Thevenin's voltage. Now the next step is to find Thevenin's resistance RTH. How will you find RTH? From this circuit, if there is a voltage source, we have to short circuit it, or in other words, we are replacing this voltage source with its internal resistance. The internal resistance for a voltage source is 0. That is, it is a short circuit. Now, what is the case if it's a current source? If it's a current source, the internal resistance will be infinity and therefore it will be an open circuit. Okay, so here since it's a voltage source, we are replacing it with internal resistance 0. That is, we are short circuiting this part. Let us short circuit this. Okay, and after this process we have to find the RTH or the resistance from this side, the effective resistance from this side, which will be RTH will be equal to, here it is R1 parallel to R2, therefore this will be equal to R1 R2 by R1 plus R2. So thus we got VTH and RTH. Now we have to draw the Thevenin's equivalent circuit. So the Thevenin's equivalent circuit will be this VTH in series with this RTH, and now we can fit the load resistance here. So we are placing that load resistance that we removed from here, this RL. Okay, so we can convert any big network into a small network like this using Thevenin's theorem, just by replacing the voltage sources and internal resistances. So now let's read this theorem. Any two-terminal linear network having a number of voltage sources and resistances can be replaced by a simple equivalent circuit. Any big circuit can be replaced by a simple equivalent circuit like this, that is consisting of a single voltage source, that is VTH here, in series with a resistance, that is RTH here, where the value of the voltage source, where the value of this VTH is equal to the open circuit voltage across the two terminals of the network. So this VTH is the open circuit voltage across the two terminals, these two terminals of the network, and resistance is equal to the equivalent resistance. Resistance is the equivalent resistance that is measured between the terminals. This is the equivalent resistance between the terminals with all the energy sources replaced by the internal resistances. That is replacing voltage source by zero internal resistance or current source by infinite internal resistance. So that is the meaning of this theorem. Today let's discuss the Norton's theorem. So this is the Norton's theorem. I'll read this theorem later. First I'll explain what it means. So consider I'm having a circuit like this. Let this be a circuit. This is RL. Let this be R2, R1 and voltage. This is the terminal A, B. So we have to find the Norton's equivalent circuit of this circuit. So the step 1 that you have to do is to take away this load resistance. Remove this load resistance. So the circuit will look like this is V, this is R2, R1 and this is the terminals A and B. So here I have taken away this RL. The next step, step 2, let this be figure 1. Step 2, I have to short circuit this AB. So that it will be like this. Let this be ISC, which is the short circuit current. This is R1, this is R2 and this is V. And now we have to find the value of this short circuited current. So in this circuit it will be, since this path is short circuited, current from this voltage source will not flow through this R2, it will flow to this path. So the circuit will be like this. This is ISC, this is R1 and this is V. Now you can find ISC equal to V by R1. So we found the value of short circuit current. Next we have to find the Norton's equivalent resistance. So for that, step 3, in step 3 I have to take this network which is figure 1. From this figure 1 I have to remove the voltage source. If there are current sources you have to open circuit them, and if there is voltage source then you have to short circuit them. This means that this process means replacing them with their internal resistance. So current source is having infinite internal resistance, so it will be open circuited, and voltage source will be having zero internal resistance, so it will be short circuited. So I am short circuiting this voltage source here and it will be like this. This figure 1 will become like this. This is A, B, this is R1 and R2. Now I have to find the Norton's resistance, which is the resistance while looking from this terminal. So it will be Rn, here will be R1 parallel to R2, which is equal to R1 R2 divided by R1 plus R2. This Norton's resistance is found in the same way as we find Thevenin's resistance. Now I got this Rn value. I am having this ISC value also. Now I can draw the Norton's equivalent circuit. So the Norton's equivalent circuit for this circuit will be, which is step 4, that will be, you have to connect the current source ISC parallel to the Norton's resistance, which is this value, and then connect the load resistance that we removed. See, now I got the Norton's equivalent circuit of this network. So this is what Norton's theorem says. Now I can read this theorem. Any two-terminal active network containing voltage sources, current sources and resistances, that is this type of network, when viewed from its output terminals, that is when viewed from this terminal AB, is equivalent to a constant current source and a parallel resistance. That is, this is the current source and the parallel resistance. That is, this circuit is equivalent to this circuit. The constant current is equal to the current which flow in a short circuit placed across the terminals. That is, when we found this ISC, we short circuited the path. So that value of current. The constant current is equal to the current which would flow in a short circuit placed across the terminals, and the parallel resistance, this resistance value. It is the resistance of the network when viewed from these open circuited terminals. That is, resistance viewed from this open circuited terminals after all voltage and current sources have been removed and replaced by their internal resistances. That is, by replacing the voltage source by short circuit and current source by open circuit. So that is what Norton's theorem says. Today we will discuss the reciprocity theorem that is used in network analysis. Let us first see what the theorem states. The theorem states that in any linear bilateral network, if a source of EMF E in any branch produces a current I in any other branch, then the same EMF E acting in the second branch would produce the same current I in the first branch. So this is reciprocity theorem. Now let us see what it means. So here the network given is a linear bilateral network. So we have to consider a linear bilateral network. So consider this network. It is a linear and bilateral network. Linear network means that in this network the relation between voltage and current is a straight line that is passing through the origin. If the voltage is in this axis and the current is in this axis, the relation between them will be a straight line that is passing through the origin. Whereas bilateral network means that it is a network that allows current flow in both directions. So here A dash denotes the input terminals and B dash denotes the output terminals. An EMF E is applied at A dash. This will produce a current I in branch B dash. Now if we interchange the position of the source and the response, it will be like this. So here the EMF is in branch B dash and it produces a current I in branch A dash. So the reciprocity theorem says that this current I in both these cases will be the same if we interchange it. So now let us verify this theorem. Consider a network like this. Let the current through branch B dash be I. We have to find this current I in this network. For that, first we have to mark the currents IT and I1, and then we have to find the total resistance of this network. So when we calculate the total resistance of this network, we will get it like this. This 2 ohm is in parallel with this 2 ohm. First 2 ohm parallel to 2 ohm, we will get it as 1 ohm. So the 1 ohm here is in series with this 2 ohm. So 1 plus 2 ohm we get it as 3 ohm. Now the 3 ohm here is in parallel with this 3 ohm. So 3 in parallel with 3 we will get it as 1.5. Now that 1.5 is in series with this 2. So 1.5 plus 2, 3.5 ohm. So total resistance RT is equal to 3.5 ohm. Now total current IT. Total current IT is equal to the total voltage 20 volt divided by resistance 3.5 ohm. So we get it as 5.71 ampere. Now we have to find this current I1 using current division rule. So I1 will be equal to this total current IT into resistance in the other branch, that is 3 ohm, divided by 3 plus the resistance of this branch. In this branch the resistance is this 2 parallel to 2, that will give 1 ohm, 1 plus 2, 3 ohm. So this 3 ohm. We will get it as IT by 2, that is equal to 5.71 divided by 2, or this is equal to 2.855 ampere. Now we have to find the current I again using the current division rule. So I will be equal to this I1 into resistance in the other branch 2 ohm by total resistance as 2 plus 2. 2 plus 2. This will again be equal to I1 by 2, which is equal to 2.855 by 2, which is equal to 1.428 ampere. So now we have to interchange the source and the response. So interchanging source and the response of this circuit, we will get it like this. We have placed the 20 volt here and we have to measure the current I dash here. So if we get I, this current I is equal to this I dash, we can say that reciprocity theorem has been verified. Let us first mark the currents IT dash here, I2 here and I dash here. Now we have to calculate the total resistance for this circuit also. So here the total resistance when we look from this side is this 2 ohm parallel to 3 ohm. So 2 parallel to 3, that will give 1.2 ohm. That 1.2 ohm is in series with 2. So 1.2 plus 2, that is equal to 3.2 ohm. That 3.2 ohm is in parallel with this 2 ohm. So 3.2 parallel to 2, you will get it as 1.23 ohm. That 1.23 ohm is in series with this 2 ohm. So 1.23 in series with 2 ohm, 3.23 ohm. So total resistance RT dash is equal to 3.23 ohm. Now we have to find IT dash is equal to voltage 20 volt divided by 3.23, that is equal to 6.191 ampere. Now again using current division rule we have to find I2. So I2 is equal to total current IT dash into the resistance in the other branch, that is this 2 ohm divided by this 2 ohm plus the resistance in this branch, that will be equal to 2 parallel to 3, 1.2, 1.2 plus 2, 3.2. So 3.2 ohm. 3.2 ohm. This is equal to, the value of IT dash is 6.191 into 2 by 5.2, which is equal to 2.3811 ampere. Now we have to find I dash. Again we have to use current division rule. So I dash is equal to this I2 into resistance in the other branch 3 ohm by 3 plus 2. So I2 we got it as 2.3811 3811 into 3 divided by 5. This will be equal to 1.428 ampere. See, we got I dash the same as I. So we can say that reciprocity theorem has been verified here. So today let's discuss maximum power transfer theorem from network theory. Okay. So this is an extended part of Thevenin's theorem. So if you want to see the Thevenin's theorem in my channel, I'll put the link in the description box. Okay. So let's see what maximum power transfer theorem says. See, if we are having a Thevenin's network, we have replaced a big network into a Thevenin equivalent, which is like this. Let this be VTH, this is RTH, and this is RL. Okay, this is RTH. Okay, we have made a big circuit into its Thevenin's equivalent circuit like this. The maximum power transfer theorem says that this particular circuit will deliver maximum power to its load on one condition, that is when RTH is equal to load resistance. So when this condition is satisfied, that is when the value of this RTH is equal to this RL, this particular circuit will have maximum power. Okay. So now let's see what is the case of an AC circuit. What happens when it's an AC circuit? Let this be Vs and let this be impedance Zs and let this be load impedance ZL. Okay. This is equal to Rs plus JXS and this is equal to RL plus JXL. Okay. So now maximum power transfer theorem in an AC circuit says that this circuit will deliver maximum power to the load impedance when ZL is Zs conjugate. Okay. So when this ZL is a conjugate of this impedance, this circuit will have maximum power. So suppose if Zs is 3 plus J4, this circuit will have maximum power when ZL is equal to 3 minus 4J. Okay, this is the conjugate of this. So in that condition, this circuit will have maximum power. So today here we are having a question from superposition theorem. We have to find the current I through this 3 ohm resistance using superposition theorem. So what does superposition theorem say? It says that let us split the current I as I dash and I double dash. Okay. So I dash is what? I dash, let us consider that I dash is the current when we are replacing this current source by an open circuit. Okay. Consider this as an open circuit. At that time, what will be the current through this 3 ohm? That is indicated by I dash. Okay. And what is I double dash? See, we are having the current source here, which is 5 ampere. We have to find I double dash. What will be I double dash? I double dash will be when this voltage source is short circuited. Okay, only current source is considered and this voltage source is short circuited. That is I double dash. Okay. So the superposition theorem says that total current I through this will be equal to I dash plus I double dash. So I dash is the current obtained by open circuiting the current source, and I double dash is obtained by short circuiting the voltage source. So we are considering only one at a time, only one source, and the other source is replaced by its internal resistance. So for a voltage source, its internal resistance is 0, so it will become a short circuit, whereas when a current source when replaced by its internal resistance will be infinity, so it's an open circuit. Okay, so we are considering the algebraic sum of the currents obtained by replacing the sources with internal resistance. So let's start doing the problem. So let's place this voltage source here. This is 20 volt. Okay, this is 20 volt. So first step is to find I dash. I dash will be obtained by open circuiting the current source. So at that time, what will be the current through this 3 ohm? So I dash will be equal to, so we don't have to consider this part, only this circuit will be there. What will be the current? The total voltage 20 volt divided by total resistance, that will be 5 plus 3 ohm. This will be equal to 20 divided by 8, or this is equal to 2.5 ampere. Okay, so in this case the current direction is like this, so we can consider it positive. Now let's consider the other case, that is when voltage source is short circuited. So I'll draw the circuit here. Voltage source is short circuited. We have resistance 5 ohm, 3 ohm, 10 ohm, the current source 5 ampere. Okay, now again we have to find the current. Let this current be, let the current that is passing through 3 ohm resistance be I double dash. Okay, so what is this I double dash? Since 5 and 3 are parallel, this 5 ampere will be coming here. Okay, this 5 ampere will get split among 3 ohm and this 5 ohm. So the value of I double dash will be equal to the total current I into resistance of the other branch 5. We are using current division rule here. So the main current 5 ampere into resistance of the other branch, that is 5 ohm here, divided by 5 ohm plus 3 ohm, which will be equal to 25 by 8, that will be equal to 3.125 ampere. Okay, here also the current direction will be in this side, will be positive. If this current direction was like this, then we could have taken this negative, but here the current direction is given as like this. Since the current source is present here, the current direction will be like this. So now what will be I? I will be equal to plus 2.5 plus 3.125, which will be equal to 5.625 ampere. So this is the current through 3 ohm resistance, and we found out this using superposition theorem. If this video has helped you, please do subscribe to my channel. Subscription is totally free. Okay, so thank you.